just because we're going to have some notes here. All right, so let's jump in. Let's talk about ampacity. So you should have an understanding, at least a little bit of ampacity. Maybe it's not the perfect understanding of it. Maybe you're still a little bit confused as to what ampacity is. Sometimes I use it sort of as an overall word to just state anything's ability to carry amperage. Right? So I might say it as the ampacity of the receptacle. Now that's a little bit incorrectly used if I say the ampacity of the receptacle. I know what I'm saying. I'm saying the receptacle has an ability to hold 15 amps if I plug in a load that has 12, 15 amps. We're all good there. Higher ampacities will then damage the receptacle. But it's more a word centered around conductors. All right, so that's the first thing to kind of understand about this word is ampacity is a wire's ability to carry amperage. So I have a definition here. We'll use this as our definition. If you got it, good. If you want to write this down, I'd say even better. Just so you understand it in a more technical way, and a lot of the ways in which the books are going to throw these words at you. So that's what it is. A few things that we know or expect when we say ampacity. Bless you. When we say ampacity, we're talking about the maximum first. Amount of amperage current, right? Just using that term. The maximum current that a conductor can carry. The other thing is continuously. So those are two things about ampacity that are givens. The amount of amperage a wire can hold for a prolonged period of time without damaging it, and that's what exceeding the temperature rating. Because the worry with amperage, the honest worry with amperage, yes, it can damage the copper on the conductor. All right, now if you're writing that, I'll sort of set up what I mean here. And I guess I'll just do it in red here. We have our conductor side, and then we have the insulation around the conductor. Because amperage is heat, heat affects things around it. But honestly, with copper, it requires a lot of heat to damage it. It takes a lot. Now, can I... I'm just checking. I thought I saw a misspelling. Can I damage copper quickly? Yes. I can do it very fast. I can take a number 12 wire and put 100 amps on it. This is way too much amperage than that copper conductor or the copper part of the wire can handle. And it will likely sever it. The heat will generate, generate so much heat that at some point along the copper part of the conductor, it will sever in half. Right, that's a lot of amperage. But the reality is that a 20 amp circuit, it is unlikely in any real normal scenario that 100 amps will show up. Now, can I build? Let's say I have 5 outlets that are on a 20 amp breaker. All right, so I have 5 outlets on one 20 amp breaker, so one number 12 going to all 5 outlets. Can I get to 100? Yes, I can get to 100 by plugging in 15 amps at a time, 15 amps at a time, and build the amperage. But at some point along the building of the amperage, specifically once I get past 20 amps, the breaker's going to trip. So when it comes to over amperage on a circuit, it's really a little bit that hangs out there more than what the wire is rated for that becomes a problem. It's not this like massive amount of amperage is going to break the wire or anything like that. But on a number 12, let's say for example, just to use it, that's rated for, let's say 25 amps if we're looking at the 90-degree column. If I were to put 27 amps on this, right? Only a little bit more amperage than the wire is rated for, but I got this magnetic field from the amperage around the conductor. The real worry is the insulation. The insulation is going to start to get damaged and at some point expose the copper inside the conductor, and then that copper can touch metal, people can get shocked, or damage equipment, etc. So that's where temperature rating comes in. It's without exceeding the temperature rating of the insulation around the conductor. Write that 5 a little better. So just to look at that whole sentence now as one, the maximum current that a conductor can carry continuously without exceeding its temperature rating. All right, any follow-ups there? Okay, good. So far, so good. Probably haven't reached anything that seems too confusing. So our goal, always, our goal is to select a conductor that can handle the load. Now, there's a few approaches to handling a load or selecting a conductor. One is continuous versus non-continuous. Right? If we're dealing with a continuous load, then we do a little bit of an increase to the load. 125% it was, just to remind you of that. It is Monday. Whoops. So, multiply by 1.25 is what we've done. And then we bump this amperage up a little bit. Not crazy, but just a little bit. I believe that's 25. I'm not 100%. Let me just do the math. It's Monday for my brain, too. I know I've done, 25. I was almost sure, but... So now I can select a breaker and a wire. So that's what we do. We focus on the load when we're going to size a conductor. So the only focus we have when it comes to sizing a conductor is how much amperage or how much current, or in other words, how much load are we going to put onto this wire and breaker. Now the breaker sets the rating of the whole circuit. 20 amp breaker, that's what the whole circuit is rated for. The load tells the breaker, the load tells the wire. So that's what we're trying to do. What we're trying to do is deal with an amount of amperage created by a load, and we're going to select a wire that can handle that amperage. Breaker we've already talked about. We'll just do a little bit more reviewing when we do it on Wednesday, but with the breaker or overcurrent protection device, we've looked at it now a few times. Now, so there are some approaches that we have from that point. All right, but good so far. Again, if there's any follow-ups. Now, we have this term called abnormal conditions. All right, an abnormal condition, of course, is something that's abnormal. What's abnormal? Not normal. So the code has two considerations for normal conditions, and that is the temperature that the wire is in and how many wires you put into a conductor. Into a conduit. If you meet those two terms, if you put the exact amount of conductors that it expects in a conduit, and you keep it at a normal temperature, that's what we call a conductor without abnormal conditions. All right, and I'm using this, or I'm giving notes around this because this is going to come up on the exam, and I don't want anybody just to get stuck on the use of some words. Without abnormal conditions means the wire is experiencing no issues. We're going to select this conductor based off of the two things that you see down here below. Very simple. More than 100 amps, you pick the wire from the 60-degree column when you size the conductor. Again, this doesn't mean when I go to the supply house that I am going to ask for the wires that are in the 60-degree column. I'm just going to ask for some number 8s. I figured out the number 8s because they are going to, let's say, a 50, 60 amp circuit, whatever, and that's in the 60-degree column where I picked the wire from. So that's how it reads. If the load is 100 amps or less, remember 100 amps or less, the conductor is selected from the 60-degree column, and if the load is 100 amps, over 100 amps, and again, that, just a side note that, which I always like to remind you, it's 101. or technically 100.5, but let's not get too technical. The conductor is selected now from the 75-degree column. Never ever is the conductor selected, not by, selected from the 90-degree column. And the reason is they just didn't exist. When they created this code section and built all this stuff around it, they just didn't exist. So here's where we are. So if I say, straightforward, because these questions are going to come as well. The easy ones, the hard ones. If I say, what size conductor is needed for a 60 amp circuit? We go simply to the 60-degree column. We find a wire that can hold 60 amps. That's the one we select. And same thing, if I say a 200 amp circuit, then we go to the 75-degree column and pick the wire from there. No abnormal conditions. Good so far.
What table is this from?
This is actually coming from article, if I'm not mistaken, 210 is where this actually shows up. I can get us the exact article if you bear with me 1 second. This was covered in Code A, should have been. So let me go over to my Code A lecture and grab that for everybody. Let's see here. Or no, did we? Sorry about that. Maybe we covered this. Maybe this was a 210. I apologize. 210. So let's see which article this is coming from. The exact article number now is escaping me. I can get us that. Yeah. I will get us that exact article. But it comes out at 210.
I thought it was 310.
No, it's not a 310. I don't believe. It's either Article 110. Yeah, because I'm almost 100% sure I did it with the Code A class recently. I'll get us that. I'll get us that article. I will get us that article. I'm just having right now a memory lapse as to when I covered this exact. Yeah, and here's where I covered it. So I forget exactly which article this steps into or mentions that, but I'll get us that article. I'll get the right number for that. And I know, and I know I recently covered it. I just don't know where. Too many classes.
I think it is 310.
Say that again?
I think it is 310.
It is out of 310 specifically? Okay, all right. Do you know?
310.16, the table. Well, I have 100 amps or less and 100 amps over written right there on that.
Great, okay, great. So maybe it is coming out of 310. It's just confusing me as to where we're getting that. Let's see here if I can find it. If it is 310, then it should be right after the table of insulation, if I'm not mistaken. But
Capacities of insulated conductors with not more than 3 carrying conductors. And then also, this was what was written down from Code A. It says for the circuit breakers, refer to 240.6.
yes, that's the size to size the circuit breaker. We got that part. I'm just trying to find the literal words from the article so that we can go here. Because I know we say it to you guys, but it comes out of a specific article where, and maybe you guys gave me an article number, I just didn't hear it, or, yeah. 1 second. Too many overlapping articles. I could head to my notes and try to do it that way. One second. as I thought. 110. Yeah. Sorry about that. 110.14. Now that rings a bell. Yeah, Article 110.14. Let me head over to it. You know, that was what I wanted to say. That's why I kept it. It's definitely a Code A thing that you learn, because I know I just taught it. I remember not teaching it to you guys. It was to the Code A class. So 110.14, and I am running over to it to point it out. But now I do exactly remember that article number. There we go. All right, there we go. Comes out of this code section here. All right, let me back up a little bit just to show you the code section. 110.14, electrical connections, because what that really is more so about is the termination points that we're using. You should have covered this, like I said, in Code A when you talked about temperature ratings for the terminals that we're landing our wires. When you splice conductors, conductors have a temperature limitation, as I was just discussing earlier. That's what the ampacity is. We could even read it right here. The temperature rating associated with the ampacity of a conductor shall be selected and coordinated so as not to exceed the lowest temperature rating of any connected termination. In other words, wherever you're terminating your wires, that's going to determine what temperature rating of conductor you'll select. Usually, they tell us this, unless otherwise specified, which happens right there, unless the equipment is listed and marked otherwise, then the ampacity used, and here we are, termination provisions for equipments for circuits rated 100 amps or less, 60 degree, and we find the 75 right after that down here with B. So let's write the actual full article for that one. It is 110.14 C. This is a real annoying one. This one is 110.14 C 1 A, and the one below it, all the same, B. All right, and even within that, it has a 1, 2. So not to get, I can also put 2 here. We can continue. So one of those forever articles.
So the 1 and 2 are included in that C?
Yes, the 1 is included. It's 1A and 1B. Yeah, so it's 110.14C, temperature limitations. 1, equipment provisions with temperature limitations. A, termination provisions for 100 amps or less. And then B, all the same things I just said, 110.14 C, temperature, B, termination points. 1 termination points B, and now this one covers 100 amps or more, or rated over 100 amps. 75 degrees.
Use like the letter front of the number. You can never use just the number 1.
You can, if that makes it easy for you, yeah.
Like 114.1 A.
Yep. You can do that. Yeah. You can put it as 1A in here. You put the A up top, something like that. And then B over here. That'll work. I guess it doesn't have to be on top. 1A, B. Yeah, whatever helps you get to that article section. But this is something we should be now at this point trying to memorize, trying to let that just become a thing we know. I know that's 100 amps or less, 60 degree. I know that 100 amps or more, 75. Over 100. Real critical that we say over 100, sorry. I just said 100 amps or more. But yeah, that's the article it comes from. I'm going to jump back over to 310, so 1 second as I get back over there. But that's specifically the article it comes in. And yes, you should have, now putting it all together, you should have learned this in Code A, or at least gotten an introduction to this in Code A. In Code A, I don't think maybe I did, threw in some temperature correction factors. We don't deal with too many abnormal conditions yet. So in the beginning, it should just be understanding selecting a wire without any abnormal conditions. If I give you an amperage, find me a wire. Straightforward. Wires are always selected from, I'll put here 31016, so we always know where we get our wires from. Always 31016. And in many cases, you're going to deal with no abnormal conditions. Even if you're running some Romex in a house, always, because Romex is not going to be in a conduit. You're in a house, so abnormal temperature conditions are not going to be, unless you're doing a house in Alaska, maybe, I don't know. Haven't worked there, so I don't know how they approach it. So, for the most part, in a practical sense, in the you working out in the field sense, no abnormal conditions in most cases. Now, of course, testing, questions, they want to know that you know the rest of the articles, so that's where we get some abnormal conditions, which we're going to look at today, highlight, and then we'll go into some questions around it. But so far, so good. Quick recap, we got ampacity is the conductor's ability to hold amperage continuously without exceeding the temperature rating of the insulation, if you wanted to even add that to your understanding of it. If we have no abnormal conditions that we're dealing with, then 60 degree or 75 based off of that 100 amps window. All right, any follow-ups there? Questions? So, just to look at 31016. Here's where we go. Right, we have our 60 degree Celsius, 75 Celsius column. Again, ignore the insulations. We are only sizing the wire. We are only saying, I have 124 amps to deal with. Then, all right, 124 puts me at over 175. I work my way down until I find a wire that can hold 123 amps or the next available size higher, which would be the number 1. No abnormal conditions. That situation is simply a number 1. Now I said again, you go to the supply house, can I have some number 1? Yes, you may. They will bring you THHN, THWN2. That's the conductor that we're selling these days, and you can see if you even look at it, it's actually that wire can hold a little bit more than those 30 that I sized it to. So this wire's got a pretty big margin of buffer in reality. This is why they introduced the 90 degree, not why, but one of the reasons they introduced the 90 degree column conductor is just better insulate. It's all it is. 90 degree column is just new, conductor 10.0 now. I don't know, we've gone through a lot of wires. It's just a better insulation than the older models. Can hold a little bit more heat. So as you can see from the column, it just gets better in the ability for the wire to hold amperage. If we're looking at that number 1 in the 60 degree column, it only holds 110 amps. If we're looking at that same wire in the 90 degree column, it jumps to 145. More temperature, or sorry, I should say higher temperature rating on the conductor gives it an ability to hold more amperage. Just a better wire. All right, so now without abnormal conditions, now let's look at the abnormal conditions. And this was just the article to point out where it comes from. This is 100, and this would be, like I said, 101. This is the column, that's the column. And I only have partial column there. I only took the amperage, so forget the size of the wires. All right, now abnormal conditions. With abnormal conditions, if we have abnormal conditions, then there's technically only 2 types. But if we have an abnormal condition, the way to understand this is, with abnormal conditions, a correction factor is applied to the ampacity of the conductor. In other words, I'm going to make an adjustment to the wire's ability to hold amperage due to one of these 2 abnormal conditions. There's only 2. more than 3 current carrying conductors in the conduit, generating heat, generating amperage, really generating the magnetic field that is around the conductor. When it has load current, when it has load amperage on it, it's going to have a good magnetic field around it. As I bunch that wire up with more and more and more wires, as I was saying last week with that scenario at that school, so many wires in a conduit, no way for the heat to go anywhere. You maxed out the amount of wires you can put in this conduit. They're all generating a ton of heat, but that heat can go nowhere. You got a 100-foot conduit run. Where does the heat in the center of that run go? Nowhere. It stays in the conduit, and it's going to affect the wire's ability to carry amperage. This wire cannot carry the same amount of amperage anymore by factors that we can multiply. So if we have too many wires, we start to add a correction factor for too many wires. Now, same thing happens to temperature. We have a temperature that we've assigned the ampacity of these conductors. These conductors, again, they come from the fact that if we come over here, ampacities of insulated conductor with not more than 3 current carrying conductors in the raceway, and 30 degrees Celsius, 86 degrees Fahrenheit. As soon as the wire is dealing with hotter temperatures than 86 Fahrenheit, then we have to, again, apply a correction factor for the temperature rating. Because again, and this is another thing we need to now memorize, amperage equals heat. Right? Amperage equals heat. And heat is the enemy, in a sense, right? That's why we have all these temperature ratings of the wires. Heat is the enemy of the insulation of the conductor. If you put it around too much heat, the insulation starts to feel the effects. And then yes, then we can lose the insulation, then we can expose the copper, and then it becomes a problem. As I said, it's not so much the worry that the wire is going to sever in half or anything like that. Yes, we can by putting a massive amount of amperage on a small little conductor, but that's not normally how that happens. Okay, good so far. Any follow-ups to any of this? Excuse me. Now, the only other thing out of Article 310 that we looked at, and it's kind of like just hidden within all of this stuff. Excuse me. And I didn't add a page for it, but I will. Let me cut the image here real quick. I was just going to go to the article, but I do want to bring the image in over here. 1 second. Because there's a note that I want to point out. If you go over to Article 310, well, it's a table. We like to say that, but it's not an article, it's a table. This table here. All right, we used this table when we were doing our load calculations last week for the single, dwelling units. And this is not specifically for one dwelling, just dwelling units. So here again, all right, because I'm gonna add some conditions to all of the wire selecting. Okay, yeah, there'll be some easy questions with no abnormal conditions, just to make sure everybody knows how to do this. But I'm gonna throw some other conditions to it. So this is the table that we would go to if we were selecting conductors for dwelling units, services, and feeders. Now we would, again, do a load count, always the load. The load dictates what size the wire has to be. All right, if you need to write that down, write it down. It's just something now to start to memorize. It's the load that I want to know. That size is my conductor. So that's why we did the whole load calculation to the house, and we came over with the kVAs of the house, and then we divided that by 240, so I'll just put E here, and we came up with an amperage for the conductor, for the home. And then we come over here and we say, what amperage are we dealing with? 100, 110, 125, etc. And now we find a wire size. But there's a note here Make sure you have this understanding. There was one more thing, yeah, out of this section, now that I just thought of it. If no adjustment or correction factors are required, meaning if there are some adjustment factors required, then we apply the adjustment factors to the house as well. All right, so all of the selections that we look at from the table 31016 from this single phase dwelling services and feeders table, all of that is with no abnormal conditions. The second some abnormal conditions come in, what is an abnormal condition? Too many wires in the conduit or too high of a temperature, then we have to adjust. Meaning if there are abnormal conditions, then we go to table 31016 and we apply the whole process, and then we select the wires from 31016. All right, we do the whole math, which we're going to do now. Now, one last thing that I wanted to mention, again, I just thought of it here, was the parallel conductors that we talked about last week. All right, we looked at conductors in parallel. These as well. We sized some conductors for the parallel. We had a few rules that we had to consider. Parallel is 1/0 or larger. We can go smaller than 1/0. All right, so we had some things that we had to deal with. We also had some things that the conductors had to consider, which is same length, same size conductor material, insulation they mean, same size, etc., etc. But also no abnormal conditions. So we did like whatever, we had 1,000 amps, and we said how many parallel 3, how many parallel 2, how many parallel 4, and we selected a bunch of wires in that regard. But again, if no abnormal conditions exist. If abnormal conditions exist, we always apply the abnormal conditions table, always. All right, because this can get a little confusing when you're selecting wires, especially when you're sitting in front of an exam and you're going, oh, which one was this one? Do we just do this? And which time, when do we use this table, etc. All right, questions? All right, so let's do this assignment. All right, practice assignment essentially, but let's do this one. All right, so let's deal with question 1. Sorry about that. Let me bring it in a little closer so that we can see it a little better. We'll deal with one question at a time, and we'll just walk our way through this. Where is that? There we go. We'll walk our way through it. We'll get the right answers, or we'll get the answers, and then we'll keep going. All right. So if anybody wants to get ahead, no problem. But we're all going to be on one at a time. So let's look at question 1. I'll give you guys a minute or a minute and a half to try to figure this out. Not a minute and a half. We'll do about a minute. I don't think I can stand idly by for a minute and a half. All right, so let's approach question 1. And here again, this is a lot of how you're going to see it framed in my exam and in your code exams as well for the National Electrical Journeyman if you decide to go that route. Find the minimum, all right? And it's the other thing here is smallest. This is the smallest wire we can use. Can we go a little bit bigger? Yes, there are reasons sometimes to do that. But as with all electrical choices, we go, what is the smallest we need? And that's what we try to make sure that we understand, that we know how to size to, the smallest. So the danger is going too small. Not too big, too small. Find the minimum size, THHN. So now I'm telling you what insulation I want. This is why I want to show you this, and this is why I went over this today. You might be tempted to go into the 75-degree column right now because you're seeing 175. And you're seeing no abnormal conditions. And wait a minute, Mr. Perez, you said if no abnormal conditions, I use the thing that we already went over to look at. No abnormal conditions, I go 75-degree column. But this question is asking me for a specific insulation. So we do that.
It's still the same, right? It's still 2
Is it still a 2/0? I didn't look at it. Let me sorry to scroll down so fast. I don't like to do that when you guys are looking, but
In the 75-degree column, the 2 aught is 175, and then in the 90-degree, it's 195.
Oh, so it ends up being the same thing for either one. Okay, good. All right, hopefully everyone is seeing what he is seeing there. We're in the 75-degree column. We happen to be at 175, but again, they're asking us for THHN. So let's look at the question real quick, make sure everybody understood what just happened. We have to find the minimum size THHN conductor here. We're sizing it to 175. We don't have any abnormal conditions to deal with, so no problems with temperature or too many wires. And so we just want to run over here to the 75-degree column, but we can't go to the 75-degree column. Now, as been pointed out, this is the same size wire. Sometimes it's not. So we want to make sure that we go to the insulation that they're asking us for.
Could be at the 90 degree.
Yeah.
Exactly. They're asking us for THHN. We're at the 90 right now.
Okay. So 195.
190.
Yes, and as was pointed out, this is going to be the same size wire.
Yeah.
Again, in this set of circumstances it was, sometimes it's not, so just holding it there for a little bit to everybody see that. So I'm going to write the answers here as we go in case you want to fill in the blanks for yourself and later use this as a study guide. So we'll go with, I'm just writing 2 aught THHN on the whiteboard, which I'll switch over to now. Now, had I not been told what insulation size or what insulation type, I go to the 75-degree column. Again, it happens to be the same wire, but if I'm given the insulation that they want me to select it from, then we go to that column where that insulation lives. If I'm not being given the insulation, then I use the rule in 11014. All right, makes sense? And questions? Okay, good, no questions. Now we're dealing with an abnormal condition. Doesn't say, we know we have an abnormal condition because we have an ambient temperature that has changed from 86. So again, I'll give us a minute here to try to answer this question. All right, so in this case, we have the situation in which we have a target amperage that we got to make sure we cover, and we have a correction factor that's going to apply to the wire. So this isn't as simple as now go over to the 90-degree column, find a wire that can hold a 145, because in that situation, it would be the number 1 that can hold 145. But 114 is going to drop, again, heat is going to reduce the wire's ability to hold the amperage. So my suggestion, if you do the divide version of this, because you can do one of two ways. You can go, all right, well, it's not going to be the 1, so I'm going to just try that 1 out with 170. I'm going to multiply it by the correction factor of 114. I happen to have the table here. 114, there's that one. TH, so this is the correction factor I want, the 0.82. And so I can then multiply 170 by the 0.82 and see if whatever this answer is, it's more than 145. If it is, then that's my wire.
I mean, what's about 170? Where do you get 170?
Oh, sorry, 145. My apologize on that one. 145. That's the number 1. Sorry, I don't know where the 170 came from.
You'd have to go up.
Yeah, do you have to go up? Oh, I know why. Now I realize where we're at. 170 because 145, if I choose the 145, I know I'm applying a correction factor to it. Sorry about that. If I choose this wire, the number 1, and I apply the correction factor, I know it's not going to be more than 145. I'm losing 18% of that wire. That's what the 0.82 is telling me. So I'm already starting at 1 wire size above it. All right, just to start somewhere, I start at already a, decision that's considering the fact that this wire is going to have the amperage reduced by a little bit. Now, I'm not going to start way up high. I'm not going to start with a 3/0 because 225 is just much larger. I'm looking for minimum. So I'm going right to that 1/0, which is 170. I multiply by the correction factor now, and yeah, as was pointed out, the number is actually too small. Just shy of 145. No good.
2
So it has to, exactly. There is, and now I don't need to do the math. I mean, if you really wanted to just go, I want to be sure, fine, but 1,000% sure. It's the 2/0.
Mr. Perez?
Yes.
For the 0.82, you got that from the first table, and then the 75-degree column?
90 degree, because the wire that we're being asked to select from is a 90 degree. We're being asked to select from the THWN2, which is a 90 degree conductor.
Okay, so wouldn't that be 0.87 then, if that's the 90 degree? Because the 75 degree is 0.82.
Its temperature is 114.
Yeah, it's 114.
No, yeah, I mean, I'm looking at it here unless I have the wrong table.
No, you gotta look at the wire, the THN.
The adjustment and the temperature, 114. That's where it's doing that. You use the 90 degree from the THN.
Oh, I'm using the wrong one. I see it. Never mind. I'm
Yeah.
looking at 13. Never mind. Sorry.
No, good, no worries. Here's where we iron out those deets. There was another question that came up, or was trying to come up, I think.
Where did that 170 come from?
Say that again?
Where did the
Oh,
170?
the 170 came from me just selecting the next size higher than 145. Yeah, it's coming over here and going, all right, 145 it won't be. The number 1 it can't be because I'm going to reduce this. So I'm just going to that next size higher, making a, decision here to go to the next one. But as I said, this can be a little bit difficult just because you got to multiply a lot. Not difficult, but it does take a little bit of time. There is another approach. All right, there is another approach. Let me just erase this bottom part here. The approach was start with the correction factor. Go find the correction factor first for 114, which is 0.82. And then instead of multiply, then divide by the amperage that you want to size the wire to. This is the division approach. And if you divide by 0.82, then you get 176.82. And so I just need a wire that's that number, which I'm not going to find, or the next size higher, which is the 2/0. I have to cover 176.82 amps. The 170 now is too small, but the 195 is perfect, the 2/0. So there is the divide approach or the multiply through the wires that you are selecting approach. Both get you to that point. The reason why a lot of teachers like to teach the multiplication one is because you're already multiplying when you do the adjusted ampacity of the wires, which we'll look at a question like that. So multiplying is sometimes the preferred method, but I like the divide method, even though it's one that you have to remember to do. So let's look at that question one more time here. Again, we were finding the smallest conductor that can manage this amperage, 145. The conductor finds itself in an abnormal condition of way too hot. So the answer, and I guess I can type the answers here for sure just to have them. 2-aught THHN. And just so once I close this and you return to this in the classroom, you'll just see the answers. And this one, coincidentally, is also a 2-aught. But THWN. Same almost. Two different approaches. The one above it, just no abnormal conditions. We still got that conductor, but this one has an abnormal condition, so we went a little bit bigger on that wire. I'll put it here. 2-aught THWN2. I'll leave that there just in case. All right, same situation, same style, insulation type. Let's try that one more time now that we got the method. Make sure we all land correctly on this one. Same situation. Find the minimum size THWN2 needed for, and now we have a different set of temperatures and a different temperature, I should say, and a different circuit amperage. So now that you have the method, you can try the divide one if you haven't used that one yet. Definitely going over to the table 31016 and going, all right, what wires come closest to 110 but a little bit bigger? Let me start there and see if after I divide the correction factor to it, it can still hold.
So Brett, the one that you sent on Google Classroom, we're not using that one?
What do you mean the one what?
Pretty much this, what do you call it, worksheet. It shows for number 3, you put conduit is in sunlight 4 inches above roof.
Oh, I got rid of that. It's okay. I didn't cover that.
Oh, okay.
Yeah, I got rid of that abnormal condition. We didn't cover it, and it gets down. I don't know. I mean, it's just down too far of conditions to worry about right now.
All right, no
Just want to make sure we understand this. But yeah, I got rid of that. Thanks. Yeah, if you printed that out, I redid the whole thing. So if you look at it now, it's a little bit different. There is a too close to the rooftop. I don't think it's necessary to go that far down abnormal conditions. But it's a just to talk about it. It's if you're too close to the roof, it's technically hotter right close to the roof. Because of tar and all the rooftop situations, they do reflect a lot of. That's what roofs do, is they kick back a lot of that heat. So as the sun is coming down with its heat, the roof is kicking that back out. That's what the roof material sometimes, paint sometimes, whatever it is that they set up there to reflect reflect off of the roof the heat, so it doesn't get into the roof. So if you have your conduit sitting right there, this is like a really hot point right there. So we actually got to consider that a little bit hotter. If you raised your conduit a little bit up a ways, then the further away the conduit is from the roof, then the less heat the conduit is dealing with by a little bit of factors. And it does affect our adjustment factor a little bit. Not too critical. I would rather you just understand correction factors and how to apply it. So if you ever get a chance to go on a rooftop, which you very likely will if you work in this industry, you'll notice that all the conduits on the rooftop are not laying on the roof. They're up off of the ground itself, or roof itself, by a little bit. All right, so do we have a conductor size for number 3?
One gauge.
Number 1, or yeah, 1 gauge is fine. Number 1 is fine too, AWG.
What was the problem again? I didn't see.
Oh, the problem? Yeah, I'll go back over to it. Yeah, make sure even if somebody's answered it, you still get there yourself too. All right, and there are cases which we think it's an and we got it wrong. Oh, somebody gets the right answer. So it's looking for THWN. It's 110 amps now, and the temperature is 117 degrees Fahrenheit, which keeps us in the same everything as last time. It's a 90-degree column conductor, THWN. 0.82 is the correction factor because 117 is almost the same as 114, really. So it's just I kind of redo to question 2, make sure you got it. These are the, and should be a number 1. All right, we go over to 310. Now, again, 2 approaches. We got 2 approaches. We got the 0.82. We already know where that's coming from. And if you don't, let me know. And I'm going to divide it by 110 because that's the target amperage that I want to hit. I want to make sure that this wire can cover.
What was the size of one? I sized up one from 1.
So we get,
134, right?
yeah. And then for the multiplication side,
so
you
you
just multiply to find something that covers the amperage.
Exactly. If you're going to do the multiply one, then, all right, so 110 is my target. If I'm going to do the multiply one, I come over here and go, all right, what's the closest wire to 110? Number 3, kind of close, a little too close to 1. Maybe I'll go to the next size.
That one got me, I think, 106.
Yes, and it's just shy. So then you know, if you land at 106, then the next size higher must be it.
Okay.
Yeah, so you and it was 106 times 0.82. Yeah, you land at 106 now and you go, all right, well, it can't be the number 2, 130, because it drops all the way down to 106. So it needs to be the 145 number 1.
Gotcha.
The divide, if you notice, we divide and we get to 134, so the next size higher conductor is also the number 1. So we can get there. Both methods get you there. And usually this is a more normal, abnormal condition. I play around with 165 degree Fahrenheit, but reality is your wires are never going to likely see stuff like that. So these are more practical, I would say, abnormal. A little bit hotter, but nothing crazy. A rooftop being 110, very, that's the summer in most places these days, I think. We may even get a higher temperature rating wire at some future time. We do have them for solar already. There's 105 and 125 Celsius rating. Okay, good so far. Everybody's got this. All right, let's change directions now. Let's change directions. And now let's deal with current carrying conductors. Okay, let's head over to question 4. Worded form helps us here now also answer these questions when we field them in an exam. Question 4 says, what is the adjusted ampacity? We now know what ampacity is, the wire's ability to handle amperage. So what is that adjusted ampacity when there are 9 current carrying conductors in the conduit? The size that we're dealing with is THW number 8. Now here I've given us a different type just to get into a different column. We don't have an ampacity right now. We're just looking for the wire size, the amperage of that wire size, and then we're going to adjust the amperage by whatever correction factor 9 wires in the conduit tell us we have to do. This is where we sort of ended last week's lecture. I think more or less.
Where do we find the 9 current carrying conductors?
That's just going to go right there. Good. So 11015C1 table. And I don't have the page, but I can tell you the page here in 1 second. Page 186.
Now, you look at how many conductors you're gonna have, so since you have 9, you multiply by 0.7.
Very good. All right, so I'll head over here to where we were at, and we'll do a little bit of math here. So yes, now the first thing we have to do is we got to go find the ampacity of a number 8 THW wherever it lives, and it happens to live in the 75-degree column, this one.
50?
Yeah,
50 times 0.7.
Is it 50? Yeah. It's 50 amps, and so we take that 50, but the wire now does a lot of, no, man, it's not a lot of conductors, but 9 is already a lot. So the wire's going to lose 30%. That's what that 70 is telling us. That wire loses 30% of its amperage capacity. So we drop to 35 amps. All right, again, correct terminology so that we don't get stumped on the exam just on the way a question is worded. That would be the worst. Sorry, just answering the last one so that we have the answers. So the ampacity of the number 8 is 50. The adjusted ampacity of that number 8 is 35. And again, in an exam, both of those answers are going to be there. 50 and 35 will be there. So if you aren't getting the terms correct, you might confuse and put the wrong answer. You go to the table 31016, you see 50, you see 50 as C, and you're like, all right, C, it has to be, there's 50. But we adjust. All right, does everyone know how we got to that 35? Everybody's good there? I know. These are going to start to get harder a little bit. These are going to be fun. It's going to be exciting. All right, follow-ups, questions on this one? We got it? Good. Now, same thing, by the way, can just be asked for a temperature correction factor. I could have bring that back. Number 8, THW, what is the adjusted ampacity with the temperature, 120 degrees Fahrenheit? We do the same thing. We find the wire, find the amperage, adjust for the temperature correction factor. If that didn't make sense, let me know. I'll repeat. 35 amps. All right, now question number 5. I'm going to give you guys a little bit of time to try to do this one. I want you to think it through. I want you to now remember what all these things were. So question 5 says, find the minimum size. So I'm looking for what is the smallest size wire I can use. And I've given you some conditions here. You have a circuit amps of 300 amps. So you got to get a wire that can deal with 300 amps. But here are the wires in the conduit. See if you guys can get to the right number. You can get there good. I'm obviously going to help you out through it, but we can step this one up a little bit. And in other words, I'm not telling you how many current carrying conductors. You need to tell me how many current carrying conductors this is.
Mr. Perez, I have a question. If we don't have the temperature, are we using that table at all or no?
We will eventually get to one where we have both conditions right below it, but no, if there's no temperature on this one, we don't have to apply it right now.
Okay, so then we're just taking however many conductors and then multiplying?
Excellent. So right now we have a target of 300 amps.
Yeah.
And going over current carrying conductors, remember, a hot conductor is current carrying, and neutrals are current carrying. Neutrals will have amperage on them. Not always all of it, but always some. All right, not always all of the amperage, just a little bit. So as long as you right now you understand, when you get to code D, you'll explore this a little bit more, get a little bit deeper. Actually, a little bit in code C as well. Mr. Williams will help you out a little bit with the amperage on a neutral. But neutrals don't always carry all the amperage. They carry an unbalance of it. But there will be. It's considered a current carrying conductor. So I have 6 phase conductors, that's 6 of them. 2 neutrals, that's 2 more, so that's a total of 8. But the grounding conductor is ignored. Grounding conductors do not have current on them.
Correct.
So we're dealing with 8 wires. All right, do we have a wire size?
4 out? 2 out?
Oh, we got some different ones. 4 and 2s.
300 times 0.7, right? And then,
You get 210.
yeah, 210, and then we gotta find where 210 would be. We're close to it.
No, so you did it the other way around. You first hit this with the multiplier, and you got to 210. So what you're now telling me is simply, you did question 4 for me. That's the adjusted ampacity, 210.
Oh, okay.
I need wires that can still cover 300 amps. So whatever wire you selected at 300 was too small. So the idea, if you're going to multiply, is you got to pick a wire high enough that after you lose 30% of it, you can still cover 300. So if you start at the wire right, and now, here's the other thing about this question to focus on. I did not give you a wire type. So we used a 75-degree column now. There's no THHN or THWN here at all. Neither here. These, I'll go back a couple. These, yes, here they're telling me, find me the THWN2 that is going to be sized here. Here, you approach it with 11014. 100 amps, or sorry, over 100 amps, so I'm in the 75-degree column. So if I come over to the 75-degree column, 310 is going to be too small, the 350 kc, that's too small. Because I'm going to take away 30% of that. Maybe the 400, because so I can start there. I can start by 335 times 0.7.
That one was too small.
Still too small. This is why I say the dividing is the best approach, because you don't have to keep multiplying and go, up too small, let me try the next one. Oh, too small, let me keep going. You could just find whatever the correction factor is and go that route. By dividing, you are adding to the 300 the 30% that you are losing, if that makes sense.
It would be a 700 kc melt.
Yeah, I was gonna say
Right,
that.
because we're at what, 428.57, so anything bigger than 428. So that would be the 420 too small, 460 very good at 700 kc mil.
Okay.
Right, there we are at 75-degree column because we are over 100 amps for sure. Now these are hard. I'm going a little bit harder now. All right, we're going one step here. There was a lot of things that we had to remember. We had to remember that we have to go to the 75-degree column. We had to remember the way to get there, to multiply or divide and all that. And then we also had to figure out what amount of current carrying conductors we had. So again, the goal is to find some wires that can hold that. So our size conductor, 700 kc mil. Now we could also parallel this and do all that. Wow, 300 amps is already.
Press. So it's always referred to the 75-degree column when you don't give us the type.
Exactly.
Got it. Is that just cause?
Well, yeah, that's because this code here tells us to do that. So
Okay.
if I don't give us a type of conductor that I want, we just always apply this.
Got it. Simple enough.
It's a lot to remember, I know, so that's why we're trying to get a little bit ahead of where our exam's going to be. And I'm going to go lighter on the exam. The final will kick it up just one step. So these might be more along the lines of the questions that you'll see on the finals, versus these will probably be how you'll see it on this exam too.
Do you see
Maybe
any
one
applications in the
So the answer.
like journeyman's or?
Yes, yeah. They go a little bit more difficult. In fact, the next question I'm going to show you is one that I still remember this, not the exact numbers, but I still remember the structure of this question being exactly like this for my journeyman exam. All right, so going back over here to question 5, let me just walk us all through that one more time. We had a amperage that we have to cover. We got to cover this amperage, 300 amps. Whenever the question says find the minimum size, going back up to the number 2 that we did, this was the same thing, but now it told us the type that they wanted. But same approach. We got an amperage that we got to cover, and we got a wire size that we got to get to do that after a correction factor for abnormal conditions has been applied. The only difference in question 5 is the abnormal conditions were too many wires versus too hot. Same, but different table. Same because it's all temperature. And in this set of conditions, we did not have a type of wire. So question 6 is a question that I remember from my journeyman exam. Not these exact numbers, but this is both correction factors applied to the conductor.
Is there a certain one we apply first?
No, either one, you'll get to the same number at the end. But you have to do one first, then come up with a number, then hit that number with the next one. Either one you do will get you to the same number. So here again, we have a target amperage, 200 amps, meaning which column are we using?
We're using the 75.
Exactly, because I did not give you a conductor type.
For our table, we're using table B, right? Because of 42 degrees Celsius.
Yeah, we're in 42 degrees Celsius, 75-degree column. So just to help you with that one, we go to the Celsius, 42, right here, and we're in the 75-degree column. And now we find our correction factor. Hey, this 0.82 is just chasing us around this whole thing. It's like, here I am again. Like, oh, can I shake you off? No. So if you figured that one, so you can do this. That's the start of this. Now, again, you want to use the divider, the multiply, either one. Here would, again, be a good idea to do the divide, because when you get to this number here, now you hit that number, divide by the correction factor for the wires. All right, this is a way more difficult question.
Mr. Perez, when would we use table B?
Which is table B?
3, 10, 15, table B, 1, 2. Sorry. The second one. That says it's ambient temperature correction factors based off of 40 degrees Celsius.
Based off, you're saying 40 degrees Celsius?
Yeah, when do we use that one?
That one's going to be for motors.
Oh, okay.
Yeah, that one's going to be when you deal with motors. Motors have an ambient, a running temperature of, I should say, motors want you to adjust the temperature if the temperature is above 40 Celsius or 104 Fahrenheit.
Okay.
Yeah. So motors are, when you tell me, like let's say I got a motor, it's whatever horsepower, and you tell me this motor operates at 20 amps when it's running. That is based off of the temperature not going over 104 degrees Fahrenheit.
All right.
If it does, then we adjust that, and again, same process. So going back over to the question, just to walk us through it as we're looking at it, we have an ambient temp of 42 degrees Celsius. I threw in Celsius to don't forget that table. And we have 7 current carrying conductors, basically the same amount percentage that we've been using so far. I haven't really made it too crazy. 7 current carrying conductors, very normal. 3 ABC plus 1 large size neutral. We could also do that if we paralleled, kept it all in one conductor. So our correction factor will be 70% or 0.7, but I'm just going to put the 0.70 so you can see it. So here would be my approach. My approach would be hit the 200 with 0.82.
249, 243.
243.9, yeah, very good. 243. I mean, we can call it 244, really. Not that close. And then, one more time.
348.
Yep, 348.57. We can almost call that 350. Annoying. 349. And now we have our wire size because 2 abnormal conditions, not just temperature. This would have been fine at temperature, but now we're also putting all these wires in a single conduit.
So the top one's temp, bottom one's.
The top one is the temperature.
Yeah.
Yeah, the 42 Celsius, and the bottom one is the 7 conductors. You could have done this the other way around. You could have done 200 divided by 0.7, come up with that answer, and then done the 0.82 to that. You could have done this either or. It gets you to the same size conductor. This number is what we're using now to size our wire. Again, this one's much harder. It applies both.
500.
500 kc mil. I'll put it here just in case someone has a bigger size wire.
It would be too small.
Now the reality is, right? Now, would you do this to a situation like would I put 7 current carrying conductors in 1 conduit if I'm already dealing with a temperature? Probably not. You can avoid it 100% by not doing that. Run 2 separate conduits, everybody in their own home. But these questions can show up, so. And here, it's just for fun, really. It is just to challenge you. I'm not going to throw this out in exam 2. Probably not even in the final, something like that. Maybe in the final. We'll see. See how exam 2 shows up, answers-wise. You guys try to get 80s. If you guys get 90s, then I'll hit you with the harder stuff.
But it has an extra credit.
Yeah, okay. That's fair. All right, anyone not get to the right size wire here? All right, last but not least, this is going to be an even harder question. I would suggest, or I would say. I'm not going to help us here now. So here's what we're doing. All right, we got to find the minimum size THHN needed for a 1,000 amp service ran in 4 parallel conductors, and let's see if that makes sense. Actually, I'm going to bump this on 1 just so it makes sense. It doesn't really make sense at 6. We'll do them at 8, right? 4 and 4. That'll be fine. We'll do 3 hots and a ground in one, 3 hots and a ground in the other, 3 hots and a ground in the other, 3 hots. So we're going to parallel this 4 times. So first things first is deal with the first half of the question, all right? Just deal with this. Don't worry about the second half. I'm going to parallel 4 times. See if you remember how to do that, 1,000 amps. And when I have that size conductor, then I switch gears and deal with the 8 conductors in the conduit.
So you're doing 3 conductors, or is that our choice? How many we want to do?
We want 4. 4.
4 parallel, but that
Yeah.
mean 2 in each, so 8, or that means 3?
Yeah. We're gonna do 8 conductors in the conduit.
Okay. Oh, I think you misunderstood what I was saying. For parallel conductors, that's 2 per parallel, right? Or 3 per parallel.
No. 4 per parallel. So
So-
for A phase, I'm gonna land 4 wires on the A phase position.
Oh, okay.
1, 2, 3, 4. All 4 of them together should be able to handle 1,000 amps. And then B phase, same thing. I'm going to put 4 wires on B phase, A, B, 4 wires. And then these are all going to be, of course, the same size conductor. And C phase, if we're looking at 3 phase.
Okay.
Yeah. But this helps me reduce the amount of conduits that I send here. So I can send less conduits by bunching these up a little bit in one conduit.
So is that what you have? You have 500? Yeah, because it's split. So here you can.
So I'll give you an easy way. You take 1,000, divide it by 4, go find that number.
So 250?
We're working exactly with THHN. Divide 1,000 by 4 and 250. Now find that wire size. But that's not the wire we want. In fact, to this 250, you can take and then divide by the correction factor. And now you have a new size wire that you're going to size this to.
And for the correction factor, we take all the wires?
Exactly. Just 8 current carrying conductors in the conduit. The number 8 is what we're factoring the correction factor around. This is the number we've been using so far. I didn't try to complicate this too much, so we should be looking at 0.70. So there's an easy way to parallel. To parallel 4 wires, divide the amperage by 4, go find that wire. But now we're putting them all we're putting 8 of them in a conduit. Again, this reduces the amount of conduits I have to use. And that way, but now that's going to make the wire a little bit bigger because I have the temperature to deal with when I have too many wires in a conduit. Harder question for sure. Let me write the answer for number 6 while I wait.
75.
Before that was 7. All right, what size wire do we have? Remember, we're in THHN. We're in THHN, meaning you're picking the 90-degree wire for me now. All right, I got my wire. I'll put it over here. All right, what do we got?
$100 or $500?
400, very good. No, 400 is correct.
Could you walk through the steps for that?
Absolutely. So first things first, again, let's deal with one half of the question first. We're only trying to figure out 4 parallel conductors for 1,000 amps. So 250 amps would work. 4 wires that can hold 250 amps. We're in the THHN column. So if we head over to the THHN column with that 250 amp goal, then the 260 would be fine. The 4-aught would be good.
Okay,
However, we got 8 current carrying conductors, so we can't really select the 4-aught yet until we take this 250 and divide it by the correction factor for 8 wires, which should be 0.7.
yeah. So we get 75.
357, yeah. 357, right?
Hold on, I think I did my math wrong. Oh, I
Okay, no
multiplied, that's my issue, I multiplied. Three 57, and then we gotta find where 357 would be, so 380 would be the next best.
And there we are with the 400 kc.
I was looking at the wrong, column.
Absolutely. Yeah, this is where, again, this is practice using this, getting to the right column, just a few, because you're remembering so many things that just which column am I supposed to be on becomes, that's why we're going easy at first. Well, like these 2 questions and like this one as well. That, you know, questions 1 through 4 would be more so what exam 2 is going to look at. Questions 5, 6, and 7 will probably have 1 of those or maybe 2 of those in the final. So before everybody heads out, just so you know, I filled in, first of all, we have this video that I've recorded, which, let me pause right